All right, so today we're diving into a really fascinating area, and I'm excited about this one. We're going to be talking about VQO, or Variational Quantum Optimization.
Yeah.
And we're going to be using the essay VQO, Variational Quantum Optimization for Complex Problem by Jörg O. Schneppat.
Yeah, it's a great essay. It lays out, a good roadmap for us to follow, talking about, how it works, where it's being used, what the future holds, all that good stuff.
Yeah, and I think one of the most interesting things about VQO, and Schneppat kind of hints at this, is it's this idea of using quantum computers to solve, problems that are just intractable for classical computers, right?
Yes.
Like they're just too difficult to solve with our, normal everyday computers. And so this idea of using, this kind of, quantum coprocessor almost, right? To speed up these calculations and to find solutions to problems that we just couldn't solve otherwise.
Yeah. And like he says, it's really about, finding the minimum value of a function, finding the lowest point in a value or minimizing the energy of a system.
Yeah.
And it's this idea of, adjusting the parameters of a quantum system, to find that minimum value.
Yeah.
And, he mentions this formula, E of theta equals, psi of theta, bra H kit psi of theta. This is the basic formula that describes, the energy of a system, for a given set of parameters.
Yeah. I mean, it's interesting too, I think, to kind of think about this in terms of, like the history of computing, right? We've always been trying to find ways to make computers faster and more efficient, right? Yeah. And quantum computing is just this next step in that evolution, right? Yeah. And VQO is a really good example of how we can take these new quantum technologies and apply them to problems that we're already trying to solve, right? So maybe we can start by just kind of like, breaking down some of the basics of quantum computing, right? Like what are the fundamental concepts that people need to understand?
Sure. So, I mean, the first thing is, you have to understand what a qubit, right? So, in classical computing, we have bits, which are either 0 or 1.
Right.
But in quantum computing, we have qubits, which can be in a superposition of 0 and 1.
Right.
So, it's like a coin that can be both heads and tails at the same time.
Right.
Until you measure it. And when you measure it, it collapses into either 0 or 1.
Yeah.
And Schneppat actually gives this mathematical representation of this superposition, right? Mm-hmm. He says, step I, equals alpha, 0 kit plus beta 1 kit.
Yeah.
And basically what that means is that, the qubit is in a state that is a linear combination of 0 and 1.
Right.
And the coefficients alpha and beta, they determine the probability of measuring 0 or 1. And so this is a really important concept in quantum computing because it allows us to do things that we can't do with classical computers.
Right.
And then the other really important concept is entanglement.
Right.
And this is where you have two or more qubits that are linked together in a way that they share the same fate.
Right.
So, if you measure one qubit and you find it to be 0, then you know instantly that the other qubit is also going to be 0.
Right.
Even if they're, miles apart.
Yeah.
And Schneppat gives this, example of this entangled state, right? He says, psi equals 1 over the square root of 2, 0, 0 kit plus 11 kit.
Right.
And basically what that means is that, the two qubits are in a state where they're either both theta or they're both 1.
Right.
But you don't know which one it's going to be until you measure one of them.
Yeah.
And then the other one instantly.
I mean, it's mind-blowing stuff. Like, I remember when I first learned about this stuff, it's just hard to wrap your head around.
It is, yeah.
But it's incredibly powerful, right?
Right.
Like these concepts of superposition and entanglement, they really are the foundation of quantum computing and they allow us to do these really incredible things. So how does VQO kind of fit into this picture, right? Like how do we use these concepts to solve, these really tough optimization problems?
So VQO it's a type of quantum algorithm called a variational quantum algorithm, or VQA.
Okay.
And the idea is that we use a classical computer to control a quantum computer. Yeah. Right. So, the classical computer is kind of like the brains of the operation.
Right.
And it's telling the quantum computer what to do.
Okay.
And the quantum computer is doing the heavy lifting, right? It's doing the quantum computations.
Yeah.
And the way that we control the quantum computer is by adjusting these parameters.
Right.
So, the classical computer will adjust the parameters of the quantum computer, and then it'll measure the output of the quantum computer.
And then it'll use that information to adjust the parameters again.
Right.
And it'll keep doing this over and over again until it finds the optimal set of parameters.
Yeah.
And this is really important because it allows us to use quantum computers to solve problems that are too difficult to solve classically.
Right.
And Schneeppat breaks down this VQA process into, these three key steps, right?
Yeah.
So, first we prepare this parameterized quantum circuit.
Right.
And this is basically a set of instructions that we're going to give to the quantum computer.
Okay.
And then we execute this circuit on a quantum computer and we take measurements.
Right.
And then we use a classical computer to optimize the parameters based on the results that we get.
Okay.
So there's a kind of iterative process where we're constantly going back and forth between the classical computer and the quantum computer.
Right.
And these parameterized quantum circuits, they're basically sequences of quantum gates.
Mm.
And these gates are the fundamental building blocks of quantum computing.
Right.
And they're controlled by these parameters.
Yeah.
And the parameters are what we're adjusting in order to optimize the circuit.
So it's kind of like a feedback loop then.
Exactly.
Like we're taking these measurements, we're feeding them back into the classical computer, and then the classical computer saying, okay, well, let's adjust these parameters, these quantum gates, and let's run it again and see what we get, and we're just kind of like, honing in on the best solution.
Yeah.
And Schneeppat kind of, emphasizes that this hybrid approach is really important right now because, quantum computers are still kind of, in their early stages of development, right? Like they're not perfect, right?
Yeah.
They're noisy and they have limited coherence times. But by kind of, letting the classical computer handle the parameter optimization, we can still make progress even though we don't have these perfect quantum computers yet.
Right.
So maybe we can talk a little bit about the theory behind VQO. Schneeppat kind of, lays out some of the mathematical and physical principles that are at play here. And he mentions this variations principle or variational principle.
Right.
And I think this is a really important concept to understand because it really is the foundation of VQO. So can you explain what this principle is and how it relates to VQO?
Sure. So the variations principle, it basically states that the ground state of a system, the lowest energy state of a system, is the state that minimizes the energy.
Okay.
And so in VQO, what we're doing is we're trying to find the ground state of a quantum system.
Right.
And we're doing that by adjusting the parameters of the system until we find the set of parameters that gives us the lowest energy. And this is where this formula that you mentioned earlier comes in, right?
Yeah.
The E of theta equals C eta theta, bra, H ket C eta theta.
Right.
And basically what that formula is telling us is that, for a given set of parameters, theta, the energy of the system is given by that expectation value.
Right.
And so the goal of VQO is to find the set of parameters that minimizes that expectation value.
Okay.
And that's how we find the ground state of the system.
I mean, it's interesting to think about like the connection to physics here, right? Like this idea of a system wanting to be in its lowest energy state.
Right.
And how we can use that principle to solve these optimization problems.
Yeah.
So how do we actually go about finding this minimum energy? Like what are the tools that we use? Schneeppat mentions these cost functions.
Right.
Can you explain what those are and how they're used in VQO?
Yeah. So cost function is basically a function that we're trying to minimize.
Oh.
And in VQO, the cost function is usually the energy of the quantum system.
Right.
And so we use classical optimization algorithms to try to find the minimum of this cost function.
Okay.
And one of the most common algorithms that we use is called gradient descent.
Right.
And the idea behind gradient descent is that we start with some initial guess for the parameters.
Okay.
And then we calculate the gradient of the cost function at that point.
Right.
And then we take a step in the direction of the negative gradient.
Okay.
And then we keep doing that over and over again until we find the minimum of the cost function.
Okay.
And Schneeppat actually gives this update rule for gradient descent, right?
Yeah.
It says, theta t plus 1 equals theta t minus eta times the gradient of E of theta t.
Right.
And basically what that means is that, we're taking our current guess for the parameters, theta t.
Right.
And then we're subtracting off a small amount, eta, times the gradient of the cost function at that point.
Right.
And that gives us our new guess for the parameters, theta t plus 1.
Okay.
And then we keep doing that over and over again until we find the minimum of the cost function.
So it's like we're kind of like sliding down the hill.
Right.
Right.
Yeah.
Like the gradient is telling us which direction to go.
Right.
And then eta is kind of like, how big of a step we take.
Right.
And Schneppat also mentions these heuristics and gradient-based optimization. Can you elaborate on that a little bit? Like what are heuristics and how are they used in this optimization process?
Yeah. So heuristics are basically, rules of thumb.
Okay.
They're not guaranteed to be optimal, but they're often very effective in practice.
Okay.
And so in VQO, we can use heuristics to help us choose the initial guess for the parameters.
Okay.
Or we can use them to guide the optimization process. Mm-hmm. And then gradient-based optimization, that's just a general term for optimization algorithms that use gradients.
Okay.
So gradient descent is an example of a gradient-based optimization algorithm.
Right.
And there are other algorithms that we can use as well.
Okay.
But they all rely on this idea of calculating gradients and using those gradients to guide the optimization process.
Yeah. And Schneppat mentions this parameter shift rule.
Right.
Can you explain what that is?
Yeah. So the parameter shift rule is a way of calculating gradients on a quantum computer.
Okay.
And the way that it works is that we basically shift the parameters of the circuit by a small amount.
Okay.
And then we measure the output of the circuit.
Right.
And then we use those measurements to calculate the gradient.
Okay.
And this is a really important technique because it allows us to calculate gradients on a quantum computer without having to do any numerical differentiation.
Right.
Which is a really important advantage because numerical differentiation can be very noisy.
Yeah.
And so the parameter shift rule gives us a way to calculate gradients that is both accurate and efficient.
Yeah. I mean, it's amazing to me that we can do these things on a quantum computer, right? Like calculate gradients.
Yeah.
It's just mind blowing.
Yeah.
Okay, so we've talked about the theory behind VQO. Maybe we can shift gears a little bit and talk about the technology. What kind of hardware are we using to run these VQO algorithms?
Yeah. So, there are a few different types of quantum computers that are being used for VQO.
Okay.
The most common type is the superconducting qubit.
Right.
And these are qubits that are made out of superconducting materials.
Okay.
And they operate at very low temperatures.
Yeah.
And they're pretty well developed at this point.
Right.
There are a lot of companies that are building superconducting quantum computers.
Yeah.
Like IBM and Google and Rigetti.
Yeah.
And they're making a lot of progress.
Yeah.
They're increasing the number of qubits that they could put on a chip.
Right.
And they're improving the coherence times of the qubits.
Right.
So superconducting qubits they're a really promising platform for VQO.
Okay.
And then another type of quantum computer that's being used for VQO is the trapped ion quantum computer.
Okay.
And these are qubits that are made out of ions that are trapped in an electromagnetic field.
Okay.
And these qubits have very long coherence times.
Right.
But they're not as well developed as superconducting qubits.
Okay.
There are only a few companies that are building trapped ion quantum computers.
Yeah.
Like IonQ and Honeywell.
Yeah.
And they're still in the early stages of development.
Right.
But they have a lot of potential.
Okay.
And then the last type of quantum computer that I'll mention is the photonic quantum computer.
Okay.
And these are qubits that are made out of photons.
Right.
Particles of light.
Yeah.
And these qubits they're very interesting because they operate at room temperature.
Right.
So you don't need to cool them down to very low temperatures like you do with superconducting qubits and trapped ion qubits.
Right.
But they're also not as well developed as the other two types of quantum computers.
Okay.
There are only a few companies that are building photonic quantum computers.
Yeah.
Like Xanadu and Sequantum.
Yeah.
And they're still in the very early stages of development.
Right.
But they have a lot of potential as well.
Yeah. I mean, it's interesting to see all these different approaches to building quantum computers, right?
No.
Like it's kind of like the early days of classical computing, right? Like there are all these different, approaches to building computers, and eventually, one architecture kind of won out.
Right.
But right now it's kind of like the Wild West, right?
Yeah.
Like there are all these different, technologies, and it's not clear which one is going to be the winner.
Right.
And Schnepp, he kind of touches on some of the limitations of current quantum hardware, right?
Right.
He mentions noise and coherence times and scalability. Can you talk about those a little bit? Like what are those limitations, and how do they impact VQO?
Yeah. So noise is a big problem in quantum computing.
Okay.
Quantum computers are very sensitive to noise.
Right.
And noise can cause errors in the computations.
Right.
And so we need to find ways to reduce noise in order to make quantum computers more reliable.
Right.
And then coherence times, those are the amount of time that a qubit can stay in a superposition state.
Right.
And the longer the coherence time, the better.
Right.
Because it means that we can do more computations before the qubit decoheres.
Right.
And so we need to find ways to increase coherence times in order to make quantum computers more powerful.
Right.
And then scalability is another big challenge.
Right. Yeah.
We want to be able to build quantum computers that have millions or even billions of qubits.
Yeah.
But that's very difficult to do.
Right.
It's a big engineering challenge.
Right.
And so we need to find ways to make quantum computers more scalable in order to really unlock their full potential.
Yeah. I mean, it's a really exciting time to be in this field, right?
Yeah.
Like there's so much potential, but there are also all these challenges that we need to overcome.
Right.
But it's moving fast, right?
Yeah.
Like the progress is just incredible.
Yeah.
So maybe we can talk a little bit about the software side of things. What kind of tools are available for building and running these VQO algorithms?
Yeah, so there are a few different software platforms that are available for VQO.
Okay.
One of the most popular platforms is called Qiskit.
Okay.
And this is a platform that was developed by IBM.
Right.
And it's an open source platform.
Okay.
So anyone can use it.
Right.
And it's a really great platform because it has a lot of features.
Yeah.
It has a visual interface that you can use to build quantum circuits.
Okay.
And it has a simulator that you can use to run those circuits on your classical computer.
Right.
And it also has a cloud-based platform that you can use to run those circuits on real quantum computers.
Okay.
So Qiskit is a really great platform for learning about quantum computing and for doing research on VQO.
Yeah.
And then another popular platform is called PennyLane.
Okay.
And this is a platform that was developed by Xanadu.
Right.
And it's also an open source platform.
Okay.
And it's a little bit different from Qiskit in that it's more focused on hybrid quantum classical computing.
Right.
So it has a lot of features for integrating quantum computations with classical computations.
Okay.
And it also has a lot of features for machine learning.
Okay.
So PennyLane is a really great platform for people who are interested in using quantum computing for machine learning.
Yeah.
And then the last platform that I'll mention is called Cirq.
Okay.
And this is a platform that was developed by Google.
Right.
And it's also an open source platform.
Okay.
And it's designed to be very efficient for running quantum circuits on Google's quantum computers.
Okay.
So if you're interested in running VQO algorithms on Google's quantum computers, then Cirq is a good platform to use. I
mean, it's amazing to see, all these open source platforms, right? Like this is a really exciting time to be in this field because, the tools they're becoming more and more accessible, right?
Right.
Like anyone can download these platforms and start learning about quantum computing and start doing research on VQO.
Yeah.
So maybe we can talk a little bit about the applications of VQO. Schnepp, he kind of goes through a whole bunch of different applications in his essay. He talks about machine learning and finance and materials science and logistics. So maybe we can just kind of go through some of these applications and talk about how VQO is being used or could be used in these different fields.
Yeah. So, I think one of the most exciting applications of VQO is in machine learning.
Right.
Um, and there are a few different ways that VQO can be used for machine learning.
Okay.
One way is to use VQO to train machine learning models.
Yeah.
Yeah. And so the idea here is that we use a quantum computer to find the optimal parameters for a machine learning model.
Right.
And this could lead to more accurate and more efficient machine learning models.
Yeah.
And another way that VQO can be used for machine learning is to develop new quantum machine learning algorithms.
Okay.
And so the idea here is that we use quantum computers to develop algorithms that are specifically designed for quantum computers.
Right.
And these algorithms could be more powerful than classical machine learning algorithms.
Right.
And so there's a lot of excitement about the potential of VQO for machine learning.
Yeah. I mean, it's interesting to think about how quantum computers could kind of revolutionize, the field of machine learning, right?
Right.
Like we're already seeing, machine learning having this huge impact on society. And if we can use quantum computers to make machine learning even more powerful, then that could really be transformative.
Yeah.
And Schneppet, he also talks about finance, right?
Right.
Like how VQO could be used in finance.
Yep.
Can you talk about that a little?
Yeah. So, I mean, one of the biggest problems in finance is portfolio optimization.
Right.
And basically what that means is, how do you allocate your assets in order to maximize your returns and minimize your risk?
Right.
And this is a very difficult problem to solve classically.
Yeah.
But it turns out that it's a problem that's well suited for quantum computers.
Okay.
And so VQO can be used to solve portfolio optimization problems.
Right.
And this could lead to better returns for investors.
Yeah.
And it could also lead to a more stable financial system.
Right.
So there's a lot of interest in using VQO for finance.
Yeah. I mean, it's interesting to think about like the potential impact of quantum computing on the financial industry, right?
Right.
Like it's a huge industry,
Yeah.
and it's one that's very data driven,
Right.
And so if we can use quantum computers to process that data more efficiently and to make better decisions, then that could have a really big impact.
Yeah.
And Schneppet, he also talks about materials science, right?
Right.
Like how VQO could be used to design new materials.
Yeah.
Can you talk about that a little bit?
Yeah. So, I mean, one of the biggest challenges in material science is finding new materials with specific properties.
Right.
Like we want to find materials that are stronger or lighter or more conductive.
Right.
And this is a very difficult problem to solve classically.
Yeah.
It's very computationally expensive to simulate the behavior of materials.
Mm-hmm.
But it turns out that quantum computers are very good at simulating the behavior of materials.
Okay.
And so VQO can be used to design new materials.
Okay.
And this could lead to the development of new materials with all sorts of amazing properties.
Yeah. I mean, it's incredible to think about like the potential of quantum computing to really kind of, revolutionize, the way that we design materials, right?
Right.
Like we're still using, a lot of the same materials that we were using, hundreds of years ago.
Right.
And quantum computing could allow us to really kind of, break free of those limitations and design materials that have, properties that we can't even imagine today.
Yeah.
And Schneppet, he also talks about logistics, right? Like how VQO could be used for things like route planning and supply chain management.